Question, what is half-life? And of course, that is going to be with respect to radioactive decay. We're going to go over an explanation of what half-life is, and then in the second half of the video, we'll go over 5 or 6 example problems where we calculate the half-life for some radioactive nuclei. Now, before we get started, please don't forget to subscribe to my channel, Step by Step Science. Get all my excellent physics, chemistry, and math videos. When I look at my analytics, I see that more than 90% of the people who watch my videos have not subscribed. Please subscribe, support my channel. Click the notifications bell, give me a thumbs up, leave me a nice positive comment, and don't forget to share this video. And of course, I made a bunch of other teaching and learning materials which you can find at my Teachers Pay Teachers website. We're looking for example problems or practice problems with the answers, notes, and some labs and other material that you can do. It's all available at my Teachers Pay Teachers website. The link is in the description below, and I've made other videos for this topic, which you can link to in the upper right-hand corner of this video, but this is half-life. So let's come up with a nice, simple definition for half-life, and that is simply that half-life is the time it takes for 1/2 of the radioactive atoms or the radioactive nuclei in a sample to decay, to undergo radioactive decay. Well, that begs the question, of course, is what is radioactive decay? So let's just review that for a moment. Radioactive decay is when you have an unstable nucleus, and that's our unstable nucleus. We have protons and neutrons in our unstable nucleus. In order to become more stable, that unstable nucleus is going to emit either some mass or some energy. Okay, and that's basically what we call radioactivity. And nuclei that do that undergo what we call radioactive decay. And the 3 most common kinds of radioactive decay are alpha decay, when a nucleus will emit an alpha particle, which is basically a helium nucleus, 2 protons and 2 neutrons together, a helium-4 nucleus, and then it could undergo beta decay, which is the most common kind of beta decay is beta minus, when an unstable nucleus will emit an electron, or we have alpha, beta, and then of course gamma, and gamma decay is when an unstable nucleus emits just some energy. Gamma rays, gamma energy. Sometimes people say gamma particles, but it's really just energy. Some examples of elements that will undergo radioactive decay are, for example, uranium-235, which is an alpha emitter. Carbon-14, which we use for radiocarbon dating, is a beta emitter. And then we have sodium-24, which will undergo gamma decay and emit some energy to become more stable. All right, so that's a brief overview for radioactive decay. Now, half-life, once again, is the time it takes for 1/2 of the radioactive nuclei in a sample to decay. Now, here are examples, or here are our radioactive nuclei. We have protons and neutrons, and we have 1, 2, 3, 4, 5, 6. We have 12 of them, and radioactive decay is a random process. We have 12. We know that after some time, after 1/2 life, that half of those 12, being 6, will have decayed. We don't know which ones. We don't know which one is going to decay first. All we know is that after 1/2 life, 6 of those will have decayed. Now, the half-life is the time it takes for half of them to decay. And there's a very large range in the half-life for radioactive nuclei. Uranium-235, for example, which is an alpha emitter, has a half-life of 7.04 times 10 to the 8 years. That's 704 million years it takes for half of a sample of uranium-235 to decay. Carbon-14 has a much shorter half-life. It's only 5,730 years approximately. That's the time it takes for half a sample of carbon-14 to decay. And sodium-24, which is our gamma emitter, the half-life is just 15 hours. So you can see there's a large range in the half-life from hundreds of millions of years to hours, and actually there are many that have much shorter half-lives, like seconds or fractions of a second, and there are some that have much higher, much longer half-lives than uranium-235, and it's 7.04 times 10 to the 8 years. But remember, it's a random process. We never know which nucleus is going to decay next. Okay, now here's a graphical representation we're going to show you of half-life and what happens. So you should be familiar with how this graph works. we have on our y-axis, we have the number of radioactive nuclei we have at the beginning that are not decayed. And you can see we have a grid over here of 10 by 10. Each dot represents a radioactive nucleus that's going to decay. And on the x-axis, we have the number of half-lives. 1, 2, 3, 4, 5. We don't know how many years it is yet. We'll talk about that later. But this is just the number of half-lives. So we have our time equals 0. We're going to say we have 100. So we're going to put a dot on our graph right there at 100 nuclei. That's the number we have. And then after one half-life, because the half-life it takes for half of them to decay, then after one half-life, we're only going to have 50 remaining that have not decayed. So the orange ones are the ones that have decayed. And after one half-life, 50 have decayed. We only have 50 white dots undecayed that have not undergone radioactive decay. So we put a dot there for, on our graph, one half-life, 50 remaining. And after another half-life, which would be 2 half-lives, after another half-life, 50 of the remaining are going to decay, and we're only going to have 25 left. So then after 2 half-lives, we put a dot there for 25, and so on. After another half-life, we're only going to have 12.5, or 12 or 13. We put another dot there, and then again, we're only going to have 6 left. You can see we have 6 there. And then after one more half-life, we're just going to have 3. And that's the dots for, those are our data points for the number that are remaining after each half-life, the ones that have not decayed. And then you can draw a nice smooth curve and you get that very nice, very common that you've probably seen exponential decay curve like that. And you can see that same thing on this table. You can see after 0 half-lives at the start, we have 100%. 1 over 1 is 100%. After 1 half-life, we have half or 50. 2 half-lives, a quarter or 25. 3 half-lives, 1/8 or 12.5%. All the way down, keep going. And then after 7 half-lives, okay, just after 7 half-lives, then you have 1/128th or 0.78125%, less than 1% remaining. So you can see it always reduces by 1/2, like that. Okay? That's how you get that exponential decay curve. Now, usually when we measure half-life, we don't measure the number of atoms. It's too hard to do that all the time. You can do that, but usually what we measure is the activity. And the activity is directly related to the number of radioactive nuclei that we have. So activity is the rate of decay expressed in units of time. And you can just say that activity is the number of decays that occur per second. All right. We have a device called a Geiger counter, which can measure the number of decays that occur per second, because it can receive those alpha, beta, and gamma particles, or energy, and it can have a sensor in there, and it can count the number of decays that occur per second. And you can see here in this picture, there's somebody measuring, okay, this is a picture from Chernobyl, measuring the radioactivity that is being emitted by this tree, and you can see it's 2,537 counts per second. All right, that's the unit, because the symbol for activity is an A, the unit is the becquerel, and 1 becquerel is 1 decay per second. And in this picture, you can see we have an activity, or the activity is 2,537 becquerels, which means every second 2,537 radioactive nuclei are decaying. And you should notice that there are 2 things that the activity is dependent upon. If you have something that's highly radioactive, when we say it's highly radioactive, it has a high activity. The activity depends on 2 things, the amount of substance and the half-life. Okay, for the amount of substance, the more substance you have, the more mass you have, the greater number of radioactive nuclei, then you're going to have a higher activity, because you're just going to have more of that material. Okay, and that means the mass and the activity are directly proportional to each other. For half-life, they're inversely proportional, because the longer the half-life, the lower the activity. If the half-life is really long, then they're not going to be decaying that often. So those 2 things are inversely proportional to each other. Okay, so that's half-life and activity. And generally when we measure half-life, we measure activity, and then the activity will decrease by 1/2 after each half-life. Okay, and you'll see that in the examples that we're going to go over in the next part of the video. Okay, so here is the first example problem we're going to do. This is number 1. It says a radioactive substance decays with a half-life of 2 days. Estimate the time after which 99.9% of the substance has decomposed or has undergone radioactive decay. So we want to know really when is there only 0.1% left. All right, so let's just write it down. You can just write these down one as we go along. At 0 half-lives, we have 100%. Okay, we're talking about percentage here. We're not talking about the number or the activity. We're talking about the percentage. Well, after 1 half-life, okay, then it's 50%. After 2 half-lives, then it's 25%. After 3 half-lives, it's 12.5. After 4 half-lives, it's 6.25. You can see I'm dividing basically each of these numbers each time by 2, because after each half-life, another half of the material is gone. So after 5 half-lives, we're down to about 3%, 6 half-lives, 1.5%, 7 half-lives, as we said earlier, 0.78%. Okay, that's not one, that's less than 1%. We want to get down to 0.1. So that's 9 half-lives. We have 1.9, and at 0.19, and after 10, it reduces to just under 0.1%. So if we want to have 99.9% of our material decayed, so we only have 0.1% left, it has to undergo 10 half-lives, and each half-life, or the half-life in this example, is 2 days, so it would take, in this case, 20 days, like that. Okay, it's basically 20 days, or you can think of it as 10 half-lives, depending on how long the half-life is. Okay, that's number 1. Number 2 is now we're going to determine what is the half-life of this material. Okay, now we've been given this graph. Here's some data somebody collected. This is the activity on this axis, on the y-axis this time. Here is the half-life, or here is the amount of time that has occurred. So this is the activity measured in becquerels. And at the very beginning, when we say, okay, now we're going to start measuring, we had an activity of 800. Then after some time later, maybe it's like 2.5 or 3 hours, we measured an activity that's around, 525 or something like that. We plot all those data points. After 6 hours, it's like 350. After maybe 20 hours, it's a little more than 100, and so on and so on. We draw the curve, and that's our exponential decay curve. And we want to know, what is the half-life? Well, the half-life is the time it takes for half to decay. Well, if we had originally an activity of 800 becquerels, after 1 half-life, because half of our nuclei have decayed, that means the activity is going to be reduced by 1/2 down to 400. So we draw a line from 400 activity, then the activity of 400, over to our graph, and then we go down to the time axis, and you can see that that time is approximately going to be about 5 hours. Okay, it is an estimation, but you can see we go over here, we get like 5 hours, and then after another half-life, then we go from 400 to 200, and you can see then that's about 10 hours on our graph, just like that. Okay, that's example number 2. Now, for example number 3, we have bismuth 199. Okay, that's the mass number, and it has a half-life of 27 days. And we want to know how much, if we start out with 992 grams, how much of our sample will be remaining after 135 days. Okay, now we know the half-life is 27 days, and we want to know 135 days. Okay, now the first thing you can do is maybe write down what you have, and you can just divide the 135 by 27, because the total time is 135. Each unit or each half-life is 27, and you can see that you get that that's going to be 5 half-lives. All right? Because 5 times 27 is 135, or 135 divided by 27 is 5. So 1 half-life, we have 100%, is 992. Excuse me, not 1 half-life, but at the beginning, 0 half-lives. Okay, and then after 1 half-life, we have half of that, which is 496. After 2 half-lives, we have 25%, or 248 grams. After 3 half-lives, 12.5%, 124. 4 half-lives, and then 5 half-lives, we have 3.125% or 31 grams. So the amount that's going to be remaining for that sample of bismuth 199 is 31 grams. Okay, example number 3. Okay, now we can go on to example number 4, and this is another example where we're going to be using a graph to determine the half-life. First, we have to plot the data we've been given over here. This is the time, and this is the activity that was measured at each of these time periods from 0 to 120 days. When we start at the beginning, we have an activity that is 62. That's like our time equals 0, so we put a dot there. Data point for 62. You can see on the y-axis here we have activity, and on the x-axis we have the time in days. Well, at 20 days, the activity has reduced to 38. And then after 60 days, it's 20, and after 90 days, it's 12, and after 120 days, now it is 8. Okay, now we see we can draw a nice smooth exponential decay curve, and we want to know what's the half-life. Well, we had originally had an activity of 62. After one half-life, then the activity is going to be reduced by 1/2 because the number of radioactive nuclei remaining is reduced by 1/2. So we go from 62 down to 31. So we're going to draw a line across to our graph. Our curve from 31, you can see we have 2031, we're approximating. And then we go down, we see what time interval corresponds to the activity being 31. And that looks like it's just about 32 days, just like that. So we can say that the half-life of that material is approximately 32 days because we can see that the activity reduced from 62 to 31 over a period of 32 days. Okay, number 5. We have a sample of Einsteinium. It has a half-life of 4.5 minutes, and we want to know what fraction will remain after 4 half-lives. Now, it doesn't say how many grams or how many of them, it just says what fraction. So we know after 4 half-lives, we could just write down like that, 0 half-lives, 1 half-life, 2, 3, 4. And we know that at the beginning, we have 100%, which we can write as 1 over 1 as a fraction. Then we have the original time, which is 0 minutes. Well, after 4.5 minutes, we have a half. After 9 minutes, it's a quarter. And after another half-life, 13.5 is an eighth. And then after 4 half-lives, we have 1/16. Okay, so we have 1/16 is remaining after 4 half-lives. Now, a lot of times we don't say 1/16. We could convert that into a fraction, into a decimal, and then into a percentage. So it's 0.0625 for a decimal, just 1 divided by 16, and we multiply that by 100, and you get 6.25% of the sample is remaining. And I think we have one more example. This one says that number 6 says over a time of 378 years, a 56-gram sample of titanium-44 decays so that only 0.875 grams remains from the original titanium-44 sample. We want to know what's the half-life, okay? Now, we've been given the total time, okay? And that's 378 years. And we want to know when it reduces from 56 grams to 0.875 grams. All right, now we're starting out with 56 grams. So we can start out with 56 when, 1 half-life or 0 half-lives. Then after 2 half-lives, it reduces to 14. And then it reduces to 7 grams, which is half of 14, and then half of that is 3.5, half of that is 1.75. So there's 1.75 grams remain after 5 half-lives, but we want to know 0.875, and that's one more half-life. That means it takes 6 half-lives to do that. That's 6 half-lives, and it takes a total of 378 years. So we can divide the 378 by 6 because it took 6 time intervals for that to occur, 6 half-lives. And you see that the half-life of titanium-44 is 63 years. Okay, so there you go. I hope you find the video helpful. Explanation and examples for half-life. If you did, please do all of the following 5 things. Please support my channel, Step by Step Science. Get all my excellent physics, chemistry, and math videos. You should, of course, click the notification bell so you don't miss anything. You should give me a thumbs up. Leave me a nice positive comment in the comment section below. And don't forget to share this video with all of your friends. Thank you so much for watching. We'll see you in the next video.